In our last section, we looked at calculus properties in terms of our vectors, so we looked at limits. In 13.6, we're going to talk about derivatives and integrals, and these properties are very similar to that of our single variable calculus. So if we look at this first diagram, I have this vector r, and r has tail at origin. Its head is going to be at this point P. Now if we look at some distance along the curve delta t, and we look at this other vector r of t plus delta t with head at point Q, what we've formed is a vector from P to Q, and that vector is called a secant vector. So it's similar to a secant line. Now imagine taking this vector r of t plus delta t, and in the second diagram we're going to move this vector closer and closer and closer to our vector r, as close as we wish. So at this point P, this vector, which I'm going to call r prime of t because it's the derivative of r, is our tangent vector. So similar to a tangent line. Now I said the tangent vector, but I really meant to say a tangent vector. Let's think about this. Any vector pointing in the same direction as r prime is tangent at the point P. It could be shorter, it could be longer, and in fact, it could be going in the opposite direction. There's actually infinitely many vectors tangent at any point on a curve. So r prime is a special vector. That is the vector that you get when you take the derivative of r, and the property is that this vector is going to point in the direction that the curve is generated. So down here in our bullet point, this derivative of r, this vector, will point in the direction of the curve. It's tangent at the point, provided that this derivative is not zero, because the zero vector has no direction. Now you imagine, let's say that we have a position function. Then r prime, the derivative, is going to be our velocity vector. And its magnitude, r prime's magnitude, is going to be the speed of the object. So a lot of application and similar applications to what we had when we looked in Calculus 1. In this box, we're going to look at how we compute the derivative given any vector, r. It can be written as a function of t in pieces, where f of t is your I component, g of t is the j, and h of t is the k component. So f, g, and h are all differentiable functions with respect to t. So to take the derivative, it's super simple. All you have to do is take the derivative of each piece. It's the same as when we computed the limit. We took the limit of each piece. In example 1, we're going to compute the derivative for r. And again, all I'm going to do is compute the derivative for each piece. So we do have to be careful. When I look at this first component on I, it's t times e to the 3t, so we have to use our product rule here. So r prime of t is going to be equal to, I'm going to do derivative keep plus keep derivative. So derivative of t is just 1. This becomes e to the 3t plus keep the t. The derivative of e to the 3t is 3e to the 3t, so this becomes 3t e to the 3t. I'm going to put this in parentheses because this whole piece is the coefficient on the I vector. And then the derivative of sine is just cosine, so this will be plus cosine of t j. And then natural log of 2t plus 5. So remember, when we look at the derivative of natural log, it's always going to be 1 over the argument times the derivative of the argument. So in this case, the derivative of 2t plus 5 is just 2. I'm just going to write 2 here. And that would be our k component. I'm actually done. So that's how you compute the derivative for a vector. Really, really simple. Let's try another example. Remember that that still has a variable t. So what this is saying, excuse me, what this is saying is for any t value, you can compute the derivative. Example 2, we're supposed to find the tangent vector for r of t, and then we're going to evaluate it for a specific t value. In this case, our vector is written in vector component form, or vector brackets. My goodness. So I'm just going to keep it in the brackets. R prime is going to be the derivative of sine of 2t is chain rule, right? So it's going to be cosine, argument stays the same, times the derivative of the argument. And that would give me 2 cosine of 2t. The derivative of cosine is negative sine. And the derivative of 4t is just 4. So I'm supposed to be evaluating this when t is equal to pi over 2. So remember, this is a function where I'm putting in pi over 2. So just be careful with your notation. And this is going to give me the vector -2, -1, 4. Cosine of 2 times pi over 2 is just cosine of pi, which is -1 times 2 would be a -1. Sine of pi over 2 is 1, so this is -1, and then 4 is constant. Again, super easy. Because there are infinitely many vectors tangent at a point, it's often helpful for us to talk about the unit tangent vector. That would be a specific vector of length 1 that's tangent at our point. And we typically use a unit tangent vector when we're really not concerned with the length of the vector. We're just looking at a direction. So to get a unit vector, we always take our vector and we divide it by its magnitude, which is why we have this formula here, that capital T vector, and we reserve capital T for the unit tangent vector. So if you see this capital T, you can assume that we're talking about the unit tangent vector. And it's simply the derivative divided by the magnitude of the derivative vector. Example 3, we're supposed to find the unit tangent vector for the parameterized curve. And then it's given to us that this is for t values greater than or equal to 0. That really doesn't matter when we compute the derivative, but if we were applying this to an application problem, we would just have to make sure that we don't put in any negative t values. So first I'm going to compute the derivative, and then I'm going to take its magnitude. So the derivative is going to be equal to 5. And in fact, why don't I just do it all at one time? So in the numerator, I'm going to have the vector 5, comma, -2 e to the -2t, comma, 3 e to the 3t. when I compute its magnitude, it's going to be the square root of 5, so that's 25, plus negative 2e to the negative 2t squared. I got to figure out what that is. Plus 3e to the 3t squared, all underneath this square root. All right, so 5, negative 2e to the negative 2t, 3e to the 3t, over 25, plus 4e to the negative 4t, plus 9e to the 6t, and that's underneath the square root. So I'm done, actually. I can't really simplify what's underneath that square root at all. So oftentimes what we'll do is, if we have a vector written in that form, we'll pull out the magnitude, and I never make my lines long enough. And we'll just multiply it by our vector. I personally don't care which way you write it, but again, my math lab might. So that's a unit tangent vector. Okay? So I'm going to call this capital T. So sometimes this just is a little bit labor intensive, but totally doable. So let's move on to example 4. We want to find the unit tangent vector for our vector r that's given, and then we're going to evaluate it when t is equal to 1. So do the same thing I did before. I'm going to compute the derivative, and then I'm going to take its magnitude. This becomes 5, 0, negative 5 over t squared. That would be my vector. And then in the denominator, I'll have 5 squared, or 25, plus negative 5 over t squared squared. All right, so that would be my unit tangent vector, and I'm not going to bother to write it by pulling out the magnitude. I'm just going to leave it like that, because the goal here is to actually find the unit tangent vector at t equal to 1, right? So I'm just looking at finding this vector when t is equal to 1. So that's what I'm going to compute. The vector 5, 0, t is 1, so this is going to be negative 5, over the square root of 25. If t is equal to 1, it's negative 5 squared, so 25. And that would give me the vector 5, 0, negative 5 over the square root of 50, which becomes 5 square root of 2. So you should simplify. And now I notice that the 5 in my vector and the 5 in the denominator can cancel, so I could actually write this in a simpler way. If I take 5 over 5 square root of 2, I have 1 over the square root of 2, 0 for my second component, and negative 1 square root of 2. So this would be a simplification that it's assumed that you're going to do, because it's an easy simplification. and we were evaluating the vector at a specific t value. So typically when you do put in some value for t, things will simplify nicely. On this page, what we're going to do is look at the derivative rules. They're similar to the rules that we have in calculus. You just have to remember that we're not working with just functions. We're working with vector functions, real functions, and constant vectors. So remember, u and v, these are vectors. But f, that's a real valued function. So it's a function in the usual sense. Oftentimes when we talk about a real value function, we'll just say scalar valued function, which just means it's a real function. And now we're also going to have this constant vector c. So if you take the derivative of a constant vector, this would be our property 1, you get the 0 vector. Similar to if you take the derivative of a constant, you get the number 0. Property 2 says that if you take the derivative of a sum of vectors, you can go ahead and take the derivative of each vector separately and then add them together. And that would be true if you were subtracting as well. You could do that separately. Example 3, we're looking at multiplying, so we got to be careful here. We're multiplying a real valued function to a vector. These are not two vectors because remember, we don't multiply vectors. We either take their dot product or their cross product, but we don't multiply them. So if you take a real function and you multiply it by a vector, then you can actually use the product rule that we normally have for real valued functions. It would be derivative keep plus keep derivative. Usually, and this is going to be true for the remaining properties, it's usually easier to combine them first, then take the derivative. So for 3, 4, 5, and 6, it's typically easier to work on the left-hand side of this equation, combine functions first, then take the derivative, as opposed to working with the right-hand side of the equation. So now in property 4, we have a composition where the inner function is a real valued function. The outer function is our vector valued function. When we compute the derivative, it's the chain rule. The derivative of the outside, inside stays the same, times the derivative of the inside. So it's the usual chain rule. 5 and 6 would be the derivative for the dot and the product of two vectors. Again, I caution you that working on the left-hand side and doing the dot or cross first is typically easiest. So if you're going to dot two vectors and take the derivative, you can use the usual product rule. It would be derivative dot keep plus keep dot derivative. But notice that on the left-hand side, I'm just doing the dot product once and then taking the derivative of the resulting value. But on the right-hand side, I'm doing the dot twice, plus I'm doing the derivative twice. So it's more efficient to work on the left-hand side, although it doesn't really matter. 6 is where I would caution you to work on the left. If you cross two vectors and take its derivative, then again, it's going to be similar to the product rule, where you're going to take the derivative, cross, keep, plus keep, cross, derivative. On the right-hand side, we're computing the derivative twice, and we're computing two cross products. And cross products are kind of intensive. So again, I would caution to probably do the cross first and then take the derivative. when we look at these properties, all of the properties will result in a vector except for 5, right? When you dot two vectors, you don't get a vector. So this is the only property where you do not get a vector. So this is not a vector. The rest of them are. Example 5, we're going to compute the derivative of this vector v. And now v of t is described as 2tj plus t squared k. But we don't want to just compute the derivative of v of t. We want to compute the derivative of v of 3t to the 4th minus 4t squared. So going up to these properties, this would be similar to property number 4, where we have a real valued function inside our vector function. So again, I'm not going to actually use the rule. I guess in a way, indirectly I am. What I'm going to do is actually figure out what this vector is first. So v of 3t to the 4th minus 4t squared, all that says, and this is a function in the normal sense, all that says is wherever you see t in our function v, replace it with 3t to the 4th minus 4t squared. So looking at my first component, it's 2 times t, so I'm going to replace the t with parentheses 3t to the 4th minus 4t squared. And that would be the component on j. Notice there's no I component here. Plus, this is a t squared, so since I'm replacing t with parentheses 3t to the 4th minus 4t squared, then I would square all of that. That would be the component on k. So I decided to compute v of 3t to the 4th minus 4t squared first, and then take the derivative. So now when I compute the derivative of 3t to the 4th minus 4t squared, the constant 2 stays. Inside the parentheses, this would just be 12t to the 3rd minus 8t. And that would be my coefficient on j, plus, so we have to use the chain rule on this next part. The 2 exponent 2 comes out in front. The 3t to the 4th minus 4t squared stays the same, minus 1 from the exponent, times the derivative of the inside, which would be in parentheses 12t to the 3rd minus 8t. And I'm actually done. However, oftentimes these can get pretty long, so you may be asked to write the form in a simpler way or in factored form. So if I was to write this vector factored, what I would do is I would look at the j and k components and factor out any common factors. So I see I could pull out a 2, and I can also pull out the 12t to the 3rd minus 8t. And there may be more that I could pull out, but for now I'm going to leave it this way and see what it looks like. So this would just be j plus parentheses 3t to the 4th minus 4t squared k. All right, on the outside of those brackets, it looks like I could factor this further. The 12t to the 3rd minus 8t, it looks like I can bring out a 4t. So if I factor out 4t, it becomes 8t parentheses 3t squared minus 2. And within the bracket, I can factor out a t squared. So again, all I'm doing is writing this completely factored, because oftentimes that's what you will need to do for my math lab. I'm not sure how picky they're going to get. Sometimes they're not very picky about this. Keep in mind that I don't care if you factor it. All right, so this would be the factored form of my vector. Sometimes it looks a little bit messier. Oftentimes we will write it using the vector brackets. We'll take out anything that factors out of both components. In this case is both j and k, or if there's an ijk, all three components. And then write the vector, the I is 0, the j is 1. And then the k would just be the t squared parentheses 3t squared minus 4. So again, just a caution that the MyLab may want you to write it in a factored form. Let's move on and compute some more derivatives. So we're just going to go through a few examples here before we look at integration. Example 6, we're supposed to compute the derivative of this cross product. And u is going to be 2t to the third I plus t minus 1j. And then v is a vector that we had before, 2tj plus t squared k. So again, I don't want to do derivatives and then do two cross products. I'm going to work on the left-hand side. What I'm going to do is I'm going to do the cross product of u cross v first. And then I'm going to go ahead and take the derivative of that resulting vector. So remember, we have our I, j, and our k. If we look at our vector u, because that's going to come first, and we look at the components I and j, we get 2t to the third for I. Our j component is t minus 1. And our k component is 0. So again, remember that when you cross, you have to do it in the direction that you're reading. If u comes first, it's going to be the first row. V comes second, it's going to be your second row. So v is simply 0 for the I, 2t for the j, and t squared for the k. So I'm going to dot. Remember what we do, we cover I, and what we get is t minus 1, 0, 2t, t squared. That would be the coefficient on our I, minus, cover the j, we get 2, t to the third, 0, 0, t squared. That's our j. So could you imagine doing this twice and using the right-hand side? Plus k would be, cover the k, you get 2t to the third, t minus 1, 0, 2t. Again, that would be your k. When we compute this cross product, we're going to get the t minus 1 times t squared. So I'm just going to distribute that t squared. So it's t to the third minus t squared. And notice that when I do minus 2t times 0, that's gone. So this is simply t to the third minus t squared. That's my I. When I look at my j component, I'm going to multiply 2t to the third times t squared, which would give me 2t to the fifth. But I have 0 on the other product, so this just becomes 2t t to the 5th j, plus multiplying 2t to the 3rd times 2t would give me 4t to the 4th. And again, minus 0, that's gone. That would be my k. So I've done the cross product. I still need to take the derivative. So u cross v, when I take the derivative, that's going to be equal to the derivative of each piece, which would give me 3t squared minus 2ti minus 10 t to the 4th j plus 16 t to the 3rd k. So in this case, it was much easier to do the cross first, then take the derivative. Now you could try it using the right-hand side of the formula. You'll get something that's super long, and then you'll have to simplify it. Let's compute the derivative of this vector. But this is going to be dotted with another vector. Okay, so we're going to compute the derivative of this dot product. Again, I could use the formula, or I could simply dot these two vectors first and then take our derivative as usual. So I am going to keep the derivative. I'm going to do the dot product first. So remember, the dot product just says multiply, add, multiply, add, multiply, add. So when I multiply the I components, I get t to the 3rd cosine of t. And now it's no longer a vector, right? So this is t to the 3rd cosine of t plus t to the -1 times -5t would give me a -5. So this turns into a -5. Again, no longer a j, it's no longer a vector. Square root of t times sine of t would just be the square plus the square root of t times sine t. And once I've done that, then I'm just taking the derivative in the usual way. So the derivative here is going to be, first we have to use our product rule. So I'm going to do derivative of t to the 3rd, so 3t squared, keep the cosine, plus keep the t to the 3rd. The cosine is negative sine. I'll clean that up later. The derivative of -5 is just 0. So now I'm going to look at the derivative of the square root of t times sine of t. Again, I have to use a product rule. So this is going to be plus 1 over 2 square root of t, the sine stays, plus square root of t stays times cosine of t. That's my derivative. I'm just going to clean it up a little bit. Remember, this is not a vector. So it looks like 3t squared cosine of t minus t to the 3rd sine of t. And then I think I'm going to write this as sine t over 2 square root of t. I'm not going to bother to rationalize denominators. Plus square root of t times cosine of t. I'm going to go ahead and stop there. I'm not going to bother to write this in factored form. Just caution again, remember this is not a vector. All right. Let's go ahead and look at integration. So we saw that derivative is easy, right? You just take the derivative of each piece. Integration is simple as well. When we're integrating a vector, and here we have our ijk vector where each component is a function of t. We're going to integrate and get this new vector. So when you take a derivative, when you take a limit, when you integrate, you get a vector. So this new vector, which we denote by capital R, it's like the capital F when we talk about an antiderivative. It's going to be the derivative of each piece. Now don't forget that if it's an indefinite integral, so there's no limits of integration, then we have to add that constant c, but these are vectors, so this is a constant vector c. Okay? So again, this is a vector. Example 8, we want to compute the integral for this function. Okay? So I'm going to integrate. And I could keep it as ijk. Now when we integrate, we have to keep it in vector form. That would be the proper form because we're integrating a vector. We don't leave off the ijk. So it's e to the 3ti plus, I'm going to write 1 over t squared as t to the negative 2j plus e to the tk. And we're taking the derivative with respect to t, so don't forget your notation. I know this is an online course, but you're still expected to use proper notation when you're showing your work. This is going to be equal to, the integral of e to the 3t is e to the 3t divided by 3. I, right? Vector I. And then t to the negative 2 is going to be t to the negative 1 over negative 1. So that turns into a minus 1 over tj plus e to the tk. And since this is an indefinite integral, I have to add my vector constant c. Okay, so remember, vector is a vector. Now let's say that you're writing this in terms of vector brackets. That's fine. You could write this as e to the 3t over 3 comma negative 1 over t comma e to the t. If you do, the constant vector is on the outside of the vector brackets. Let's do another example. Example 9, we want to find the function r that satisfies this given condition. So it's not asking me to find the integral. What it's giving me is it's giving me a derivative, and then it's saying to find the function, not the derivative. And we have these initial conditions. So similar to what we did in calculus, we have to integrate the derivative to get back to the original function. So my function r is simply the integral of r prime. So I'm going to use the vector brackets. Again, remember that this is a vector, so we should keep the notation on this. We're integrating a vector, not a real valued function. And then when I integrate, I get t to the 3rd over 3. As a vector, it's going to be 2t squared over 2, so that's t squared, and 7t plus my constant vector that I need to solve for. But I have initial conditions. I know that when I take this vector function r and I evaluate it when t is 2, that that's going to be the vector 1, 6, 0. So all I have to do is take my vector, substitute in 2, and I'll have 1, 6, 0 is going to be equal to the vector 8 over 3, comma, 4, comma, 14, plus my constant vector. So this, at this point, all we're doing is solving for our constant vector. Because this solution we have here with the constant vector, remember that's just a general solution. That's not the specific solution that corresponds to my initial value, that r of 2 is the vector 1, 6, 0. Solving this equation, I could subtract the 8 over 3, 4, and the 14 from each side. So what is 1 minus 8 thirds? That's negative 5 thirds? I think I have to get a new pen. And then 6 minus 4 would give me 2. 0 minus 14 would be a negative 14. And that would be my constant vector, which means our function, given those initial conditions, would be the vector, remember all we're doing is replacing the constant vector, so that's t to the third over 3, comma, t squared, comma, 7t, plus the vector negative 5 thirds, comma, 2, comma, negative 14. And from the previous section, we know that we typically don't keep our vectors in that form. We would combine the two vectors to write this as t to the third. Oh, good, the denominators are the same. So I'm just going to write this as t to the third minus 5 all over 3 as my first component. And this is comma t squared plus 2. Comma 7t minus 14. So again, typically we would like to combine this and write it as a single vector. Moving on to our definite integrals. Exactly the same as indefinite integrals. You integrate each piece separately. But then you have to evaluate it for some t values. Okay. So typically you could split it up into the integral with respect to the I, the integral with respect to the j, and the integral with respect to the k. So like doing derivatives, you could break these all up. But it's really not necessary to write it that way. You could just look at this. So example 10, I have this integral from 0 to pi of sine I cosine 2tj plus 3tk. So technically I can split this up into 3 integrals, but I don't have to, because when I look at this I say, oh, well, the antiderivative or the integral for sine is simply negative cosine. But it's the I component. And then the integral or antiderivative for cosine of 2t is going to be sine of 2t divided by 2. So plus sine 2t divided by 2. You can always break it up into smaller pieces if you wish. And I would only do that if one of my components, I, j, or k, needed a special technique to integrate. Like maybe I needed to do a u substitution on the I or the j or the k. Then I would split it up into separate integrals. In this case, it's not necessary. The last component is going to be 3t squared over 2k. But we're evaluating this from 0 to pi. So at this point, since each component I, j, and k is going to be evaluated from 0 to pi, I do not need to split this up into separate pieces. The only reason why I would do that, again, is if I was using a special technique for one or more of the components and my limits of integration changed. So putting in pi, this becomes negative cosine of pi, which would be a negative 1. That's the vector I. Sine of 2 pi over 2 is 0. So this becomes plus, and I'll go ahead and write the 0j even though it's not necessary. And 3 pi squared over 2, not much I can do with that. That would be my k component. So it's always upper limit minus the lower limit. Putting in 0 for t, cosine of 0 is 1. So this becomes a negative I. Putting in 0 for t, I get a 0 for my j. So again, I'm going to write it just for now. I don't really have to. And then putting in 0 for t on the k component, again, that's going to be 0 as well. Combining this, I get 2i, no j's, and then plus 3 pi squared over 2k. And because it's a definite integral, I don't have that constant c. So that's something that people tend to forget, that the only reason why we need the constant vector c is if it's a indefinite integral with no limits of integration. Once you have limits of integration, then you don't have a constant at the end. Okay? So let me show you what this would look like if I used vector notation, only because in the previous example, I kept the vector notation inside. So I just want to remind you that you need to keep the vectors inside. That would be the proper way to write it. And then that would, after we complete, that would be the vector 2 comma 0 comma 3 pi squared over 2. And I know in physics, oftentimes they want it in IJK form. For mathematics, oftentimes we'll want to keep it with the vector brackets because it's actually cleaner. And that's it for 13.6.